Good day everybody, and welcome again to another video of Smarter Studio. And today we're going to dive into the Saw VCO that I developed for VCV Rack. Actually, I developed a couple of pretty baseline VCOs. The Sine VCO, for which I already published a video. The Saw VCO is the second one. And I also have a triangle VCO and a pulse or square wave VCO. All these four VCOs deliver a pretty basic foundation of functionality, like they all are polyphonic, they all support volume, phase and frequency modulation. You can all tune them, set a baseline phase, set a baseline volume. But there are a few differences which are not that entirely obvious. So in this particular video, I'm only going to focus on the delta, mostly of the Saw VCO functionality compared to the Sine VCO, and demonstrate a few of these things in this particular, well, if you like, tutorial. As said in my other tutorials about the modules that I developed for VCV Rack, this is not a tutorial about modular synthesis or synthesis in general, although a few topics will come along, let's say, during the journey, but I would not like to claim that I'm an expert, or even not mediocre, around VCV Rack or modular synthesis in general. There are far better people around there and active on the internet, like Omri Cohen, but others as well, that are far more knowledgeable in that space than I. But I think I have a reasonable understanding of the stuff I developed, and therefore let's go into the tutorial about the Saw VCO. But how you use it creatively and musically is more up to you. So, without further ado, let's dive into the tutorial. And here you see my template environment, which is not quite spectacular. Just have a mixer with auxiliary output through Plateau, which is an excellent reverb module. Basic MIDI in and out, audio amplification, output unit, a few scopes and an analyzer, and go look and see how everything works from that angle. So here I have a standard layout to have at least a tone. So I have the Saw VCO. Let's do the standard value. We have an ADSR module and a VCA all connected in the standard way, if you like, and we should be able to produce a tone using the laptop keyboard here. And as you can see, we have tone polyphonic with a maximum of 4 channels in this particular configuration. And as you can see, let me switch on the trigger here. You can see a perfectly nice triangle as long as I keep a key pressed. So as said, I'm not going into all the nitty-gritty details, because you can look at my Sine VCO to get a more detailed explanation and possibilities around the knobs that you see over here. But there's a few things that are different, and also a few things that are really particular to the way I implemented the Saw VCO, and there's things happening in the background that are not relevant for a sine wave, but they are relevant for what I would call mathematically correct, but physically impossible type of waves. And I think the Sawtooth is one of those mathematically correct type of waves, but which are physically, the way I modeled it in the software, not entirely possible. So let me try to illustrate that again, by just hitting a key and look at the telescope here. And you really see the sawtooth with a line going up, straight down, ramping up, straight down. And that is a type of audio signal that would be impossible to reproduce by a natural audio system where we have speakers with membranes vibrating as per the wave that's going through the electrical cables. It is impossible for a membrane to vibrate the way that is the exact mathematical sawtooth. But we can in software still mimic something like that. So far, okay, a lot of theoretical mumbo jumbo, but how does that really cut out? Well, if I pull a cable from my sawtooth output to the analyzer, you see a lot of frequencies being in there. And let me just tune it down a little bit to a C2. So a lot lower notes. Let's zoom in a little bit on the graph here. And here you see all the harmonics. And harmonics means actually frequencies, sine wave frequencies that are present in the whole spectrum of a sawtooth. And that's a lot. So effectively the sawtooth is physically built up as a bundle of different sine waves of different frequencies in different energy or volume ratios in such a way that they mathematically represent a sine wave. But there is a problem with that, especially with the higher frequencies, and you can actually make that audible, and that has to do with the fact that the sampling rate of VCV Rack, which is currently set to 48 kilohertz, and by the laws of physics it means that any sine wave that has a higher frequency than half your sampling rate, so 4 kilohertz in this particular setup, it cannot be sampled correctly back and sampled back into a signal that represents the actual original input signal. So the output in the digital world would be that the sawtooth wave will have frequencies in there of harmonic sine waves that cannot be sampled back to the right frequency and therefore get sampled back to a wrong frequency. That frequency is called an alias. And let me see if I can make that audible. And you can really hear it a little bit, but you have to have good ears, and maybe on YouTube it's not really audible, but you can definitely see it in the graph. Instead of having a nice curve going down, which you seem to have in this lower frequency, if I go one octave higher, it looks like the ramp stops here and then goes down back to frequencies lower in the spectrum. Those are actually aliases. The ramp should continue over here, but because the sampling rate is too low, those higher frequencies are not sampled back correctly and mimic themselves or are aliasing themselves. They're an alias of a different frequency and they come back as lower frequencies, sometimes in the audible range. And that's why you sometimes see these jumps in pitch, or they look like jumps in pitch. And here, with these notes, you can really clearly hear a faint note in the background that is actually lower than the main pitch, and those are really called by those aliases. And if you look at the analyzer, you see lots of stuff bouncing back and forth and representing as aliasing, and in the lower notes that is getting less. And you can only resolve that by putting your sample frequency a lot higher. So let me temporarily do that. Let me put the sample rate instead of 48, put it on 119 too. And then you see, even with a higher note, a much nicer graph. But at the moment, the waves go out of the audible range. You see them coming back again. So increasing the sample rate doesn't really help reducing aliases in the grand scheme of things. It may reduce it in a particular piece of music or situation, but you only shifting the horizon from one frequency to another frequency at a certain moment, because we are sampling at a discrete rate. There could potentially always be frequencies that bounce back as an alias and coming back in the audible range, and therefore giving a slightly different tone or timbre experience than the actual natural physical wave would actually do. So aliasing is not necessarily a bad thing, but it is something to take into account, that specific waveforms, especially the ones that have just a mathematical, theoretical form, cannot be 100% correctly reproduced in a physical audio system. And therefore it will introduce aliasing. That can be a charming thing, but sometimes it can also be annoying, if you like. So how can you avoid aliasing if it's really necessary? Well, again, going back into theory, any signal that is not band limited, i.e. band limited means that there is a maximum sine wave frequency in all the collection of the harmonics of a particular wave, but has actually an unlimited amount of different sine wave frequencies, you cannot reproduce it. Whatever sample rate you're using, there will be aliasing in some way, shape or form. As long as they're outside the audible spectrum, nobody really cares. In most situations, I would say. But at some point in time, they will fall back in the audible spectrum. But if you make a sawtooth wave or a triangle wave or any wave that has a non-continuous jump, either in direction or actually even in space, and a sawtooth has a jump in space, it goes up, 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 and then it, boom, it goes down. And mathematically, the time that it moves from the upper part of the ramp, it moves down to 0 again, or whatever the starting value is. If that time is unlimitedly small, it means you have a discontinuous step in the function of the sawtooth, and therefore it means you need an unlimited amount of sine waves to actually reproduce that jump, and therefore your signal is not band limited and you cannot reproduce 100% correctly by sampling and, or let's say adding sine waves in some way, shape or form. But if you would agree to say, hey, I'm not going to assume 100% drop, but it could be a kind of a gradual drop, you can also achieve that by constructing something that looks close to a sine wave, to a sawtooth, but is actually built up of a limited amount of sine waves in the right ratio, in the right harmonic ratios. And then you come into the realm of the band limited signals, and those can be reproduced a lot better without aliasing effects. And that's what you can do with the sawtooth. That's really a lot of theory behind it, and let me know in the comments if you're interested in more in-depth discussion about aliasing. I've some baseline knowledge about aliasing in sound, but also in image synthesis. So in computer graphics, you also have aliasing effects in many ways, shapes or forms. Most noticeably jagged edges on graphics. The diagonal line is blocky in theory because you have pixels, but there is an aliasing theory behind it, which also has to do with sampling and reconstruction of a not band limited signal. Again, let's stop with the theory. Let's see how you can do that in the Saw VCO and get rid of some type of aliasing. So I've added that in the right-hand menu button. So you press the right-hand menu button, you will see three options. First is ramp up or down. That speaks for itself. If we select up, which is the default, you see the ramp going up, and obviously we go down, it goes the other way around. There's, as far as I can tell, no audible difference if you're just listening to a clean sawtooth wave. It can become interesting if you're starting, of course, to play with phase modulation. When mixing multiple sawtooth waves, then up and down can actually make a difference. If one of the signals is up and the other is down, then you can get some different timbral effects. Let's go back to up. Let's look at the other part of the menu. There we have the band unlimited, which is the default, which basically is the mathematically correct sawtooth, but which has aliasing issues. But you can also go to band limited. And at the moment you select band limited, it means that you can set the number of harmonics, sine wave harmonics, that are used to generate the sawtooth. If you look at the formula for a sawtooth, it's a formula where you have the basic sine wave, then double the frequency, 3 times the frequency, 4 times the frequency in ratios that are added on top of each other to generate a sawtooth wave. So if I just select one harmonic, it's actually only the bass note, which is actually just a sine. So you can see we have a perfect sine wave, and it also sounds pretty dull and not very rich in tone, because it's just a single sine wave which can be reproduced perfectly correct without any aliasing. Now if I would go to 2 harmonics, it would mean that a second sine wave of double the frequency but with a different volume level is added on top. And you see now it sounds a bit richer. We see the 2 harmonics, and you see that it's still far from a sawtooth, but at least it's already starting to view with a bit of fantasy as a kind of triangle thing a bit more. Now let's add another harmonic. So now we have 3. And indeed we see 3 spikes in the analyzer, and you can see it's getting a little bit closer to a triangle again. And we can go to 4. Same thing, and you see that not only the graph is looking more and more like a triangle, but the sound is also becoming sharper, brighter, and more sounding like a sawtooth wave. So let's go to 10. And of course there's still the jagged edges here, but it's really kind of sawtooth already, and we only have 10 harmonics. And here you see that it's in the analyzer that the graph is really far away from the top of the bandwidth, so we're still far from aliasing artifacts. And if I really go higher, really very high, even getting out of range, you see nothing producing any aliasing. It's perfectly fine, and I can even go, let's say, go to 20, which is the highest amount of harmonics you can use here. It's still not a perfect triangle. Let's zoom in a little bit. You still see the jags, but from an audible perspective, it's pretty close to what you would hear with a theoretical one. Let me go to band unlimited. Still a bit sharper. But here you have terrible aliasing already. Not necessarily audible, but there is quite a bit of aliasing. And if I go to limited, the sound difference is not really that much, but we're still far from aliasing over here. So in that sense, I hope that I've shown to you that even going to a mathematically incorrect sawtooth by just adding the first 20 harmonics of the mathematical definition of a sawtooth expressed as in adding sine waves on top of each other. It's really not that audible as a big difference, and therefore, if you would need to avoid aliasing, I would recommend use a sawtooth that's not mathematically entirely correct, but it is not necessarily fully alias free, because really in the high frequencies you can still get some aliasing popping up, but in the general musical application of a sawtooth wave, you pretty much can stay away from any aliasing artifacts. So that's the Saw VCO. Again, for all the other functions, I would like to refer to the sine wave VCO. Let me know in the comments, as I said, if you want to know a bit more in depth about aliasing, what's the theory behind it, why does it occur, what, if anything, can you do about it, pretty much in the digital world, but also digital hardware synthesizers can suffer from aliasing artifacts. And again, it's not necessarily a bad thing, because it can add some charm to it, but there are situations where it's really generating some very weird artifacts that are not musically of any value. But we'll come to that later, because I am also working on a VCO where you can simply choose your harmonics yourselves and stack up a bundle of sine waves, choose the levels, the ratios, the frequencies independently for each harmonic, and in that particular situation you can have really strange alias behavior if you don't know exactly what you're doing, especially definitely in the higher notes, where you think you are playing the chromatic scale, for instance, and then suddenly halfway down or halfway up the chromatic scale you hear the VCO making a jump downwards in frequency, because suddenly one of the harmonics aliases back to a much lower frequency, and that can sometimes be very audible and also very unwanted and unpleasant. Anyway, that's it for the Saw VCO. Similar video will be out soon for the Triangle VCO and the DOS VCO. Let me know if you want to hear anything else, if you have any additions, comments on the VCO itself. If not, thank you for watching and enjoy making nice music. Thank you, take care, and until the next video.